Welcome back to Mathematic 59, where I'm getting more and more addicted to making videos. Some of them may even be good. This is about as simplistic as a simple situation as I could find with related rates, which is a very understated calculus topic. Basically, what you want to do is you want to relate something like an area or a volume to a length. But there's also plenty of other applications. In this particular case, a spherical ball, maybe a beach ball, maybe I can even draw it. It's losing air. And of course, as it loses air, it's losing air at a constant rate. We can state this derivative as a known constant, but what you got to realize is this change is being applied in regards to time. Now, cc is cubic centimeters. So this ball is losing air fast. Now, you can also relate volume to radius. Now, there is a formula that you should be keeping in your notes. Now, keep in mind that there is a derivative of volume with respect to rate or radius, but you're trying to determine how fast the radius is shrinking. Oh, it's losing volume, so maybe I should make that a negative. Now, if you want to take a derivative or express a derivative in regards to time, you use implicit differentiation because you don't really want to worry about the function, even though the function is a linear situation. The derivative of the sphere formula would be 4/3 pi times 3 times the radius squared. But once again, you're trying to determine radius with respect to time. So we have to consider the change in radius with respect to time. Now we're also given that in case 1, radius is 10 centimeters. So when the radius is 10 centimeters, we do know that dV/dt is always -5 cubic centimeter minute. And hang on a second. Let me make that a little bit neater. And that equals to 4 pi, because we're going to cancel out the 3's, 4 pi times 10 centimeters squared. And then we're looking for dr/dt. Now, you're going to end up dividing both sides. And when we divide both sides, your situation is going to evolve into just centimeters per minute. But we're going to go ahead and divide -5 by what looks like 4 times 10 squared times pi. And that's just going to become centimeters per minute. Now this will reduce down to our final answer, which the final answer is going to be -5 over 400 pi or -1 over 80 pi, which is a radius that's actually shrinking quite slowly, but ultimately it is shrinking. Now that's the situation for when the ball radius is at 10. Now later on, the ball radius is at 5. If the ball radius changes, all I'm going to do is I'm just going to change the 10 to 5. But what's going to happen is that's going to become -5 over 100, which really shrinks down to -1 over 20. So the radius is now shrinking faster. Now, where you might find this stuff important, maybe you've always wondered why when you see tires deflate, they don't make a big difference at the outgoing, but as the tire gets flatter, the air goes out faster and the tire looks flatter. This might give you a little insight as to why. So anyway, this is one example of a related rates problem. This problem, let me get a better. This is the 20-foot ladder. And since it's against the wall, here's the wall. And here's the direction it's getting pulled away from the wall. So what's going to happen is, as the ladder gets pulled away from the wall, the guy on top is going to fall. I don't know. I've told folks in the past that that's Romeo at the top of the ladder. Juliet is over here in the window. And down here is Juliet's dad pulling the ladder away. But might be too graphic. But we want to determine how fast he's falling when the ladder's getting pulled away. Now, because this is a Pythagorean relationship, it's going to be Pythagorean theorem. We already know the ladder is 20. It's X and Y that are going to change. And it looks like X is going to grow and Y is going to shrink. So we're going to go ahead and just state that dx dt is 1.5 feet per second. That's going to lead to Y being a negative value. Now, to take the derivative of this situation, once again, you want to relate all of these variables to time. So we're going to go ahead and take the derivatives of each term and then relate them all to feet per second. The derivative of 20 is 0. Now, if z squared had been a changing variable, you'd also have a dz dt. Now, some folks like to continue without the 2's because you can divide everything by 2's. Now, we do know that in situation 1, x is 10. Now, you can measure it and figure out that y is 20 squared minus 10 squared. And you could factor out 10 squared, and the answer would be 10 square root 3. Or you could just plug in it. You could put that in your TI-30XS and get the answer. So what's going to happen is x is 10, dx is 1.5, y is 10 square root 3, and then dy dt, and then it equals 0. This turns into a linear equation, and I could cancel out the 10s because all the numbers divide by 10. dy dt, I'm going to end up getting dy dt. I'm going to subtract the 1.5, and then I'm going to divide by the square root of 3. Now, that's not necessarily a rationalized expression, but frankly, I'm not terribly worried at this point. If you're really concerned, however, it would become negative 1.5 square root 3 over 3, and that actually would reduce down to negative square root 3 over 2. So the ladder at this stage in the game is falling at negative 3.2 feet per second. So that's a pretty fast drop. Now, for the second situation, once again, I'm going to have to change some numbers, but this time around, this one's going to take a little more work and thinking. So let's look at the case of 19 feet away. So I'm going to go ahead and do a lot of erasing, but only from here. If X were changed to 19, which means now he's way down here instead of way up there. And the ladder's probably going to be, let me get a better situation. The ladder's probably way over here now at 19 feet away. X is 19. Y would be square root of 20 squared minus 19 squared. A little bit of math will help me determine that that's a square root of 39, which is still 6 feet up or so. But he is moving a lot faster. So let me go ahead and plug in those values. X is 19. Dx dt remains constant. Y is square root of 39. And then you have dy dt. This one will also, I could also subtract 19 times 1.5. My calculator says it's 28 and a half. And I'm going to eventually divide by square root of 39. Now, if I take my calculator and work that problem out, you're going to find out that the velocity has substantially increased. But I got to figure this out. Here it is. Oops, wrong number. Let me try it again. It's negative 28.5 divided by square root of 39, not 36. It is negative 4.56 feet per second. So it's falling a lot faster. Whereas on the old, when I had the square root of 3 over 2, that particular value was still less than negative 1. So it was falling slower. So yes, as the ladder gets further out, the man on the top is going to fall a lot faster. And in fact, his speed is actually going to be an asymptotic function. Think about why. Anyway, make sure you enjoy these videos, enjoy all the color, and we'll see you on the next one.